All right, welcome to the first lecture. We're going to talk a little bit in the abstract. First, we'll start with this idea of an expression. So for us, we'll try to keep the definition simple. An expression is just some combination of mathematical symbols that allows us to use the verb evaluate, which means get a numerical value of. So an easy example, if I take 7 minus 4, then 7 minus 4 is just going to become 3, and we understand that's a thing. And we can consult a calculator and say, what is 7 minus 4? It will tell us 3. Nothing interesting here. But if we want to get a little bit more interesting, and we want to say something like 3x plus 1, and we want to evaluate that. Now, if we ask the calculator 3x plus 1, it just tells us 3x plus 1. And of course, we understand this philosophically, that until we know what x is, we can't know what 3x plus 1 is. So it turns out when you have a variable in an expression, in contrast to a constant, which has a fixed value, and we can evaluate anything with constants in it, if you have a variable, you must first determine the value of said variable to be able to evaluate the expression. So we can take a steps over here and say, if x equals 4, for example, then I can say 3x plus 1 is going to be 3 times. I will substitute the value 4 into the variable x. 3 times 4 is 12, then plus 1, and that will come out to be 13. We have successfully evaluated the expression. So in the calculator, we can do something like this, where I say, if I take x, and I do colon equals, so I'm defining the value of x to be 4. Then I can say 3x plus 1, and you notice the x is now in bold because it understands that x has a value. It tells us 13, and life is good. Okay. When you're evaluating an expression with a variable in it, you have to first figure out what the value of each variable is. And of course, we can have an expression with multiple variables. For example, I can say something like 3x squared over, we'll go with 2x plus y. And in this case, I can't just know what x is. I also have to know what y is. We have to specify the values of all the variables in the expression. So what if I do this? What if I say x equals 4 and let's say y equals negative 8? Then I can say 3x squared over 2x plus y is equal 3 times 4 squared is 3 times 16, all divided by 2 times 4 is 8, plus negative 8. Well, then I have a situation where I say this is equal to 48 over 0. And I have to ask myself, what exactly is 48 over 0? Let's consult a calculator and see what happens. If I keep x as 4 and I define y to be negative 8, and then I try to evaluate the expression 3x squared divided by, in parentheses, 2x plus y. Let's see what happens. It gives me undefined. Right? The calculator can't evaluate this, just like we can't evaluate this, because dividing by 0 is not a valid operation. So this is undefined. And as a result, we say this expression cannot be evaluated for this combination of x and y. All right, that was simple enough. Now let's consider a new idea, an equation. So an equation takes an expression and makes it equal to another expression. For example, we can say 3x plus 8 equals 11. In this context, the verb that we're interested in is solve. So the verb solve, we might more formally say as find the set of all values x that satisfy the equation. And such a set we would refer to as the solution set. Okay. So our goal is to find all the values of x that will make this equation true. Now, we could guess and check. We could say, well, what if x is 1? So if x is equal 1, then 3x plus 8 would equal 3 times 1, performing the substitution, plus 8, which is equal to 11. Oh, and because 11 is what we wanted, we would say that this value of x is a solution to the equation. X equals 1 is a solution. And in contrast, if we tried something else, let's try if x equals 4. Then, if I try to do 3x plus 8, I substitute the 4 into the x. I get 3 times 4 is 12 plus 8, which is equal to 20. And since 20, which is going to be the value of this expression, is not equal to 11, we would say, oh, this x equals 4 is not a solution. Okay, so as a result, we can start thinking about, is guessing really efficient? I mean, sometimes guessing might be a good place to start, but in most cases, we would rather come up with a method to find the solution without having to guess. And that's where we use the properties of equality. We learned that if we have an equation, then we can perform the same operation to both sides of the equation and produce an equivalent equation. So for example, I can subtract 8 from both sides. 3x plus 8, subtract 8 gets rid of the 8. 11 subtract 8 gets me 3. And I can divide both sides of the equation by the same thing, which gets me x if I divide by 3, and then 1 if I divide by 3. Now, why did I choose to divide by 3? Because at the end, I'm trying to establish what x is, because I want to find the values of x that satisfy the equation. So this act, we often call this isolating the variable, because if I can get it down to just the variable equals, then I know that this is not only a solution, it's all of the solutions, because this equation is equivalent to the original equation since we used these things called the properties of equality. So we know that x equals 1 is the only solution. And that's very powerful. This constitutes a proof. All right, now what if we want to get a little bit more advanced? And we say, what if there's an equation that has more than one solution? So let's consider the following equation, solve. And I'm going to say x squared minus 2x equals 15. And we would not like to guess. So maybe we recall that when we learned about quadratic equations, and we know it's quadratic because of this x squared, a common strategy was to get an equivalent equation where there's an equals 0. So what I'm going to do is subtract 15 from both sides. So I'll have x squared minus 2x minus 15, and that will equal 0. And from here, I want to do a thing called factor, which means find two expressions. Each of these is going to be called a factor. Find two expressions that will multiply to make this expression. And perhaps we remember that if we have the x and the x here, x times x will make x squared. And in order to make these other ones, we want to find two numbers that add up to negative 2 and multiply to make negative 15. So good candidates are positive 3 and negative 5. And perhaps you can verify that if you were to take these and distribute them out by the method we often call FOIL, then you will get this expression. Now, from here, we use a little bit of logic, and we say, this is an expression which has a value. This is also an expression which has a value, and I'm multiplying two values to make 0. The only way that can happen is if one of those, or both of them, are 0. So if this is 0, then I have x plus 3 equals 0, or if this is 0, then x minus 5 is equal to 0. And then using the properties of equality, I can say, oh, that means x is equal to negative 3, and x is equal 5. And because I've used logic and properties of equality, and that logic was sound, we are able to say that x equals negative 3 and 5 are the only solutions to the equation. And we can represent this in set notation. We can say the solution set as x is an element of the set of the two values negative 3 and 5. And so with a calculator, this one has a computer algebra system in it. So we can even do things like this, where we type solve x squared minus 2x equals 15, and we put comma x to indicate we are trying to solve for the variable x, and if we hit enter, it tells us x equals negative 3 or x equals 5. All right, so far so good. Now, what if we consider a case where I have two variables? So I'm going to say an equation with two variables. Y equals 3x plus 8. Now, here's the tricky part. If I were to naively ask you, what is the value of x that makes this equation true? Perhaps you would object. I don't know what y is, so how can I know what x is if I don't know what 3x plus 8 is equal to? And you'd be correct. And so the issue here is, in order to narrow down x to a single value, I need to know what y is first. So perhaps I can say, if y equals, we'll go with 17, then, and I can say 17 is equal 3x plus 8. And now I'm down to an equation with one variable, and we've already done something like this. I want to use the properties of equality. So I subtract 8 from both sides. I get 9 equals 3x. I want to isolate x, so I divide both sides by 3. I get 3 equals x. Now the key here is x equals 3 is a solution, but only when y equals 17. So the combination, we would say x comma y in an ordered pair is equal to 3 comma 17 is a solution. Now, what if I consider another case? What if I say just if x equals negative 2, say, then I can come up with y equals 3 times negative 2, performing the substitution, is negative 6 plus 8, and then I can evaluate the right-hand side and get y equals 2. So y equals 2 is a solution when x equals negative 2 is a solution. It's the combination that makes the solution. So I would say x comma y is equal negative 2 comma 2 in that order is a solution. So we start asking ourselves, okay, we found two solutions fairly quickly. Are there more? Well, for every value of x we pick, we're able to evaluate this expression and get a value for y. And then for every value of y we pick, we're able to solve this equation with one variable and get a value for x. It feels like we can generate combinations of x and y that will be a solution to this equation forever. There are infinitely many solutions. So now it's not so nice to start listing solutions out because I don't have the time to sit here and write infinitely many things. It's not possible. So we come up with an interesting way to deal with this. We say, what if we make a graph? So I'm going to say graph the solution set in the xy plane. So what I'm going to do is I'm going to pull up the calculator, add a graph page, and then change the graph entry edit mode to just relation. And I'm going to say the relation that I want, keeping in mind, is y equals 3x plus 8. And it produced the graph of a line. Now, perhaps you remember that if you have a y equals mx plus b type equation, then the graph of the solution set looks like a line. And here's the reason. If I were to start sort of cataloging possible solutions, I might say, okay, well, what if x is, we'll start with negative 1, 0, 1, 2, and 3. If x is negative 1, you substitute negative 1, and you get that y is negative 3 plus 8, which is 5. And then when x is 0, 3 times 0 plus 8 is 8. And when x is 1, 3 times 1 plus 8 is 11. When x is 2, 3 times 2 is 6, plus 8 is 14, and then we keep going. We notice something. Every time x changes, I'm changing the number here and then multiplying it by 3, which means every time x increases by 1, y increases by 3 times that amount, plus 3. When x increases by 1, y increases by plus 3. So if I were to take this and graph it in the xy plane, I would have negative 1 comma 5, sorry, up here, and then 0 comma 8, 1 comma 11, and so on and so on. And I recognize this pattern that every time x increases by 1, meaning I advance toward the right by 1, then y is going to increase by 3. And there's no rule in math that says I can only increase by exactly 1 at a time. I could increase by a fraction of 1. And so perhaps I would end up filling out the space in between these, but I would always maintain the ratio that for every time x increases by a certain amount, y increases by 3 times that amount because of this 3. And that will generate the shape of a line. Meaning every point on this line is a combination of x and y values that satisfies this equation. And because of this structure, we say that there's a delta x, the change in the x-coordinate, which we call the run, and there's a delta y, the change in the y-coordinate that we call the rise, and then we say there's an idea called slope, which we often use the letter m to represent. Slope is the rise over run, which is the change in y over the change in x, and that is this right here. Hence, we often write y equals mx plus b. Okay, so that's how to represent a solution set of an equation that has infinitely many solutions. Now, what if we upgrade the discussion to multiple equations? So what if I have the verb solve, and I'm going to have y equals 3x plus 8, and I'm also going to have y equals x minus 2. And I'm going to put a curly brace here to indicate that both of these equations together forms a system of equations. Okay. So we have to ask ourselves, what does it mean to be a solution to the system? Well, if we consult this equation, we can sketch the solution set as a line with a slope of 3, and then when x is 0, y is 3 times 0 plus 8, which is 8. So I know I have a point 0, comma 8, and a rise over run of 3 over 1. So I'm going to look something like this. And this right here, there's a hidden 1 there. So the slope is 1, and when x is 0, y is 0 minus 2. So I'm going to start at 0, comma negative 2, and my slope is going to be, rise over run is 1 over 1. And we can graph this here as y equals x minus 2. All right, and I'm going to zoom out just a little bit so we see where the lines intersect. Now, perhaps you remember that the solution to this system of equations has to do with the intersection. The logic behind this is every point on this line is a combination of x and y that is a solution to this equation. This is the graph for y equals 3x plus 8. Every point on this line is a combination of x and y values that is a solution to the bottom equation. This is the graph for y equals x minus 2. So the argument then is, if you are a point that is simultaneously on both of the lines, hence the intersection point, then that point represents a combination of x and y that is simultaneously a solution to the top equation and the bottom equation. And that is the solution to the system. Okay. Now, because we have a calculator, we can do things like menu, and then we can analyze the graph, and we can find the intersection, and lower bound, upper bound. It tells us that the intersection is negative 5, comma, negative 7. And if we had graph paper and nice measuring tools, perhaps we could produce the same result by hand. However, we won't always have a calculator, and we won't always have nice measuring tools. We would like to be able to find this solution just by using the equations. So, perhaps you will remember the word substitution. We've used it earlier to indicate that we're substituting values in for variables, but here we're saying, okay, if we're looking for a combination of x and y that satisfies both the top and the bottom equation, that means we're looking for a single value of y that's the same in both, and a single value of x that's the same in both, which means this y, which is equal to that expression, and this y, which is equal to that expression, are the same y. So by substitution, we can write 3x plus 8 equals 1x minus 2. And these two values of x are the same x. And so we can use the properties of equality to say, I would like to combine like terms. I want to subtract x from both sides, so I'll get 2x over here, and then this x is gone. I want to subtract 8 from both sides, so this 8 is gone, and I have negative 10 over here. Then I want to isolate x, so I'm going to divide by 2. I get x equals negative 5. Okay. But we're not done yet, because remember, a solution to a system of equations with two variables is a combination of x and y. So we found the x. Now that allows us to evaluate this expression, and we know that y is equal to that expression. So we say y equals 3 times negative 5, which is negative 15, then plus 8, so we have y equals negative 7. And thus we understand that the combination of values x equals negative 5 and y equals negative 7, x and y, is the solution to this system of equations. Let's consider another interesting case where we have a system of equations we want to solve. We're going to go with y equals x minus 2, and the other one is going to be x squared plus 3x. Let's go with plus 4. Okay. Now, perhaps we don't remember how to graph quadratic equations very easily. Perhaps remember that they are parabolas, and at some point in the future, we will come back and talk about how to graph those. But for now, all I'm going to do is I'm going to replace this with y equals x squared plus 3x plus 4 and let the calculator do the graphing for us. Okay. So this blue curve is going to be the graph of y equals x squared plus 3x plus 4, and the red line is going to be the graph of this equation. Now, we notice something. There does not appear to be an intersection. And I can zoom out up here and get a better view of it. It looks like they will never intersect. So, the theory is every point on this blue curve is a combination of x and y that's a solution to the bottom equation. Every point on the red line is a combination of x and y values that's a solution to the top equation. If I want to be a solution to both equations at once, I have to be a point that's both on the curve and on the line, meaning they have to intersect. But they don't intersect, which means there's no real solution. Let's confirm that analytically. So we're going to use the substitution method. We are going to say x minus 2 is equal to y, but that same y value is equal to x squared plus 3x plus 4. So we're going to say x minus 2 equals x squared plus 3x plus 4. Now, we recognize that this is a quadratic equation, and remember the strategy is we want to get 0 on one side of the equation. So if we subtract x, we get 2x here, and if we add 2, we get 6. This is going to be 0. Now, last time we factored, and perhaps I can sit here and try to factor, and maybe I won't come up with a clever factorization, because there isn't an easy one. And so perhaps you remember when this happens, there's a nifty trick called the quadratic formula, which the way it works is it's based on completing the square. It's a formula that does the process of completing the square, and it goes like this. We say if ax squared plus bx plus c is equal to 0 for constants a, b, and c, then the solutions are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we apply this formula to the given problem, we will have x equals negative b, which is going to be negative 2, plus or minus the square root of b squared, which is 2 squared, minus 4 times a, which is 1, times c, which is 6. So 4 times 1 times 6 is 24, all over 2 times a, which is 2 times 1. Now, when we look at this, we notice that 4 minus 24 is a negative number. So we would end up saying negative 2 plus or minus the square root of negative 20 all over 2. And perhaps you remember that if we try to take the square root of a negative number, we cannot get a real value. We specifically defined a thing called an imaginary number to just discuss cases like this, but imaginary numbers don't show up in the regular xy plane. So we would say that there are no real solutions, no real numbers for x that will satisfy both equations at once. But if there are no real values of x, then there's no real number I can put here, which means there's no real number I can get for y. So there are no real solutions. And so this is the way you think about it. If you have multiple equations in a system and you want to solve the system, you are looking for the intersections of the graphs of the solution sets. A lot of words. If you cannot get an intersection, that means there are no real combinations of the variables that satisfy all of the equations. So here we have sort of a combination of some very simple philosophy on what is an expression, what can we do with it? We can evaluate an expression. What is an equation? Well, now it's an expression equals another expression. And what can we do with an equation? We can solve it. Sometimes we can have many solutions to an equation. Sometimes we can have multiple equations and look for solutions. Sometimes we can have no solutions. And notice in the process, we're coming back and using techniques we learned, such as the properties of equality, factoring, and the quadratic formula. So hopefully at this stage, we can do some problems and refresh your memory on any of the techniques that we learned in the past that you might have forgotten. Good luck. I'll see you next time.